All right, should we start now?
Let's do it.
Let's do it. Okay. Hello, everyone. Welcome to the second day of the CHAMPS Exoplanet Early Career Highlight Seminar. Today we have an exciting session, and the morning session is going to be on atmospheres of exoplanets and brown dwarf. And the session moderator is Jason Williams. And Jason, please take it off from here.
Hey, thank you, Ravi. So first, my name is Jason Williams. I'm a fifth year graduate student at Carnegie Observatories, also at University of Southern California. And our first speaker today will be Yoni Brande, who is a second year grad student at the University of Kansas.
Okay, thanks for the introduction, Jason. Good morning, everybody. I'm Yoni Brande, and I'm a second-year graduate student at the University of Kansas. I'm happy to be here presenting some work I've done to characterize the atmosphere of the super Neptune TOI 674b. So TOI 674b orbits a small red dwarf star, 42% size at the sun, about 150 light years away. The planet is 5.2 Earth radius, 23.6 Earth mass, has a period 1.9 days, and is about 635 Kelvin. It was discovered in the first year of the test mission from sectors 9 and 10 and got our attention for further study for a few reasons. Planets the size of Neptune and a bit bigger are very uncommon at these short orbits. So here I have a plot of the so-called Neptune desert showing you where TOI 674b is compared to other similar sized planets. And you can see that there's this really notable gap in the planet period mass phase space. So there are several explanations as to why there's so few planets here. Some of the common ones are photoevaporative processes, stripping atmospheres, and a lot of really intense planetary migration. But these sort of competing explanations mean we need a lot of data to really figure out why these planets are where they are. So following this, we decided to use Hubble to spectroscopically observe the planet's atmosphere. We got 3 transits for it, and when we were looking at the data, we needed to correct for the strong systematics that WIFC3 spatially scanned light curves often have. So we modified the well-known existing model ramp method in order to fit both directions of the spatial scan at the same time, which gives us some efficiency improvements by having the number of parameters you otherwise would have need to fit the 2 scan directions separately. In principle, the sinusoidal trend that we used can be applied to other similar systematic models for Hubble WIFC3 stuff, but here's how we used it. We also got a third sector of test data, sector 36, that wasn't available for the discovery paper. So we refit that and refined the planet transit parameters for future characterization of the planet. And we had a Spitzer transit that was also used in the discovery paper at 4.5 microns to help inform our final observed transit spectrum. We looked at the possible absorbers that we could have for observations in this bandpass. And we used Paul Moliere's Petite Rad transcode to perform our atmospheric retrievals, including the Tess and Spitzer data. And we fit for absorber abundances for water vapor, methane, carbon monoxide, carbon dioxide, and ammonia. And we also fit for the planet's surface gravity and the planet's size and the planet temperature and the cloud top pressure. And this cloud model was just a uniform opaque gray cloud.
Just really quick, Yoni, you have 2 minutes.
Yeah, okay. So we compared our models, including all of these absorbers, to models with only a single absorber removed in order to calculate Bayes factor for the presence of these particular species. The only species that met the significance criteria was water vapor at a Bayes factor of 3.2, corresponding to about a 2.1 sigma detection, and none of the other absorbers were significant. So here's the final observed spectrum and the best fit model. You can see that there is some tantalizing excess absorption at the 1.4 micron, where we expect water vapor to be, and our best fit model parameters are also shown. So we think we see water vapor in this atmosphere, which is really exciting. This has only been done for a handful of these similar planets before, and especially since this one is actually in the Neptune desert, you sort of get the amusing combination of water in the desert, and that helps the media push. But our logical next step is to actually do some more serious science with this. So we want to look for things like atmospheric escape with metastable helium at 1.08 micron. We can do this with Hubble, as has been shown in the past, but we can also do it with these really big ground-based telescopes, which take a little bit more effort to propose for. But if we find atmospheric evaporation, this could be indication that TY674 is on its way out of the desert. We also couldn't precisely measure how much water is in the atmosphere of TY674b. Hubble data is just too low res to actually get this done. But we actually think we have a good chance with James Webb Cycle 2 to actually get this done and measure things like metallicities and precise absorber abundances and disambiguate the low metallicity cloud case from the high metallicity clear case. So we're really excited about the future prospects of this planet, and we'll see how it turns out. And that's all I had. So.
Awesome. Thank you so much, Yoni, for your talk. We'll jump right into questions. So the first question is from Jake Taylor. He says, great talk. Your sigma is at 2.1, the border of non-detection, weak detection. Did you test to see if this water detection goes away when changing your priors, as Bayesian evidence is prior dependent?
Yeah, so we did. It really depends. Sorry, it really depends on what the prior ranges are. I think I had a slide here that actually showed the ranges that we used. How do I get back here? Yeah, so for the absorbers, we actually went to the extreme bounds of the abundance grid that the Petite Radtrans has. So basically, these are in mass fractions. So we go from basically entirely whatever the absorber is down to 10 to the minus 6, whatever the absorber is. And those seemed fairly robust. There was a little bit of change when you mess with the temperature prior, not to destroy the significance of the results or anything, but just that you can find non-physical temperatures that are outside the bounds of what we actually expect for this planet. So we did a little bit of playing around with it, but I would be interested to see to what extent a reviewer would suggest changes here.
Okay, great. Thank you, Yoni. We have one more question from Lily Anderson. She said, do you try fitting a flat line to the spectrum? And if so, what was that fit like compared to the full model?
So in order to compare, at least with this Bayes factor method, compare a flat line, basically what we're doing is we're removing all of the absorbers and only looking for basically the cloud top and hydrogen and helium continuum absorption. That's not directly comparable to this strategy, but I did do it separately. And the featureless model, including none of these absorbers, is much less significant than a model including any of the absorbers. I think the real way to do this is to do chi-squared comparisons, but that is a different question than looking for the presence of the individual absorbers. So again, we'll see how far a reviewer pushes on that, but it's something that we did do.
Okay, awesome. And so I guess I'll ask the last question. So in the meantime, Anjali, if you could prepare your slides and turn on your face cam. I had a quick question. You mentioned at the end there about Hubble having too low of a resolution. Could you, I guess, sort of speak to if you have sort of any like firsthand knowledge, or what's sort of a good resolution that you'd be able to retrieve these abundances at?
Well, really, I think what we want to do is to be able to disentangle those big, large methane features out at like 2 and 3 micron, and have something where we can actually get our, so James Webb has I don't know, spectral resolution of something like 700 in these bands, and also significantly better precision on those. And you can see the error bars here were something on the order of like 70 or 80 or 100 ppm. So shrinking those, I think, plus more longer wavelength sensitivity would really help us out the most here. Sorry if I was not precise when I was.
No. That makes total sense. Thank you. Thank you. Okay, great. So thank you so much, Yoni, for your talk. And next we have Anjali Piette, who's at the University of Cambridge, and yeah, she'll be talking to us next.
Hi, thanks for the introduction. So yeah, my name's Anjali Piette, and I'll be talking about thermal and radiative properties of exoplanet atmospheres across the mass range. So just in October, I started as a Carnegie postdoctoral fellow at the Carnegie Earth and Planets Laboratory, working with Piette. He's giving a talk later today, so definitely check that out. But I very recently just finished my PhD working with Niku Madhusudan at the University of Cambridge. So I'll be talking to you about some of the work that I did during my PhD. So as the title suggests, I'm going to be talking about some different exoplanet atmospheres across the mass range. And I think all the really lovely talks we've had so far have really been a testament to the diversity of the exoplanet population. And in particular, I think the atmospheres of these exoplanets are a great window into studying the chemistry and the thermal properties of these planets. The atmosphere can also encode some information about the planet's formation and evolution. And in some cases, we can even use the atmosphere as a window to study the deeper physics of the planet and potentially even consider different surface conditions. So in my thesis, I actually worked on various different cases along the mass range, starting with brown dwarfs and atmospheric retrievals of brown dwarfs, and then sliding down the mass scale gradually, looking at hot Jupiters and then mini Neptunes and rocky exoplanets. In the interest of time, I'm just going to focus on these last two today. So I'm going to start off talking about the thermal and radiative properties of mini Neptune atmospheres. And as we all know, mini Neptunes are currently the most common type of exoplanet that have been detected to date, even though we don't have any in our own solar system. So that's really interesting and gives us a reason to want to understand what's going on there. And in recent years, it's become possible to characterize the atmospheres of these mini Neptunes. So for example, here on the right, I'm showing the transmission spectrum of K218b, which was recently measured, and a water detection was made with this transmission spectrum. Another really interesting aspect of mini Neptunes is that given their masses and radii, there are several different internal structures that are possible and that are consistent with those masses and radii. So for example, some mini Neptunes are both consistent with a volatile rich interior with a thick water layer, but at the same time, they could also be explained by a more rocky interior. So that's something very interesting as well. So in this work, we wanted to explore the different conditions that we can get in mini Neptune atmospheres. And we did this using a self-consistent 1D atmospheric model. So the model that we're using is an adaptation of the Genesis model that was developed by Gandhi and Madhusudan in 2017. And the idea here is that we want to understand the physics in the atmosphere and how that affects the temperature profile and the thermal emission spectrum of the atmosphere. So in the model, we have the energetic boundary conditions at the top and the bottom of the atmosphere. So at the top is the stellar irradiation, and at the bottom, we have the internal heat flux. We can also consider the different sources of opacity in the atmosphere due to different chemical species and molecules, and also optical scattering and opacity due to clouds and hazes. So the model that we're looking at here solves radiative convective equilibrium, hydrostatic equilibrium, and thermochemical equilibrium to find the temperature profile of the atmosphere given these conditions. And using radiative transfer, we also calculate the thermal emission spectrum of the atmosphere emerging from the top. So we've looked at a range of different conditions. I don't have time to go through everything today, but I'll just point out some of our key results. First of all, on this plot in the bottom right, the top row of temperature profiles I'm showing are for a clear atmosphere, and the bottom row are for a hazy atmosphere. So one cool feature that I just wanted to point out is that the presence of optical scattering, in this case due to haze, but we also see this as a result of clouds, is that first of all, the temperature profile is obviously cooler, which makes sense because the optical scattering is removing some of the stellar irradiation at the top. But also we're seeing much more isothermal temperature profiles, which means that with the presence of haze, for example, we can continue fairly cool temperatures quite deep down into the atmosphere, which could have implications for surface conditions if there is a surface beneath the atmosphere. Speaking of which, one question that we wanted to consider is, I mentioned before that these mini Neptunes are consistent with different possible internal structures. And one of those possibilities is a structure where you have an iron silicate core in the center with a volatile rich, so possibly a water-rich layer on top of that, and then with a hydrogen-helium atmosphere above that. And so the question is, depending on the pressure at which we have the boundary between the water layer and the atmosphere, and depending on the temperature conditions at the base of the atmosphere, can we consider the phase that the water would be at that surface? So could we have liquid water, like an ocean, or would it be too hot? Would we have a supercritical water ocean instead? And so to study this, it's interesting to look at the mini Neptune K218b. As you may know already, this is a habitable zone mini Neptune, and I showed the transmission spectrum on the other slide. And in work that we did in Madhusudan et al. 2020, we used internal structure models for K218b and found that if we assume this kind of internal structure, it is possible the mass and radius of K218b is consistent with a surface between the water layer and the atmosphere that is at sufficiently low pressures that water could exist at that surface. And so in this work, we wanted to go into more detail into the atmospheric conditions and see how that could affect the conditions at this sort of water surface. So we considered a few different scenarios, and I'm going to show you one of the end member cases here. So if you imagine a water ocean at your surface, naturally, you might imagine that water evaporates from that surface and increases the abundance of water vapor in the atmosphere. And now one of the effects of that is that it's going to increase the greenhouse effect in the atmosphere and warm up your atmosphere. But then the question is that warmer atmosphere still consistent with the presence of an ocean, or would it be too hot? But in fact, we find that if you include some haze opacity, or indeed cloud opacity, but in this particular example, where we're looking at haze opacity, you can actually cool the atmosphere enough that you can have a temperature profile which is consistent with an ocean, a liquid water surface at the base. And so here I'm showing examples for an ocean at 1 bar or 100 bar. So we're assuming that the boundary between the water layer and the atmosphere occurs at these particular pressures, and just seeing what temperature the atmosphere is at that pressure. So these different colors are considering different haze abundances. Here on the right, we're also considering different internal temperatures, and there are a range of conditions that allow us to have this, this liquid water ocean at the base. So to conclude this first part of the talk, we find that optical scattering from clouds and hazes is really important to consider when we're thinking about the possible surface conditions in these temperate mini Neptunes. It could make the difference between, for example, a liquid water ocean or supercritical, for example. We also find that in the case of K218b, or maybe mini Neptunes similar to K218b, there are atmospheric conditions that could lead to liquid water oceans beneath the atmosphere. And finally, I don't have time to go into a huge amount of detail right now, but we also find in the paper that JWST will be able to measure the photospheric temperatures of some of these very cool temperate mini Neptunes. And having that sort of data point of what's the temperature in the photosphere using the thermal emission spectrum, that could give us some initial clues as to what kind of surfaces could be lying beneath that atmosphere. So now I'm going to move on to the second half of the talk on atmospheric retrievals of rocky exoplanet emission spectra. And this is work that I did both with my supervisor, Niku Madhusudan, and also my collaborator, Avi Mandel. So thank you to them. So in atmospheric retrievals of giant exoplanets or brown dwarfs as well, it obviously makes sense to assume that the background gas in the atmosphere is hydrogen, of course. And so the way that that's often treated in a retrieval is that you can parameterize your model by the abundances of all your other species like water, CO2, etc. And then you say that the abundance of hydrogen is just 1 minus the rest. And that makes sense, obviously, in these hydrogen-rich atmospheres. But when we start to look at secondary atmospheres instead, we can't make that assumption because, of course, there are such a wide range of compositions that are possible for these secondary atmospheres. And so Bennett and Seeger 2012 started to use a new parameterization for these abundances called the centered log ratio parameterization, or CLR. And the idea is that by using this parameterization for all of the different chemical species in the model, the prior probability distribution for each species is identical. So that's what's shown by these blue prior probability distributions are the same for all 3 species, unlike if you assume a given background, in which case you get the black lines instead. So this CLR parameterization has been used in transmission retrievals in the past, by Bennett and Seeger 2012 and 2013, and more recently by Weltbanks and Madhusudan 2021. Luis Weltbanks is giving his dissertation talk later today, so definitely check that out as well. And so in these retrievals of rocky exoplanets, we consider a variety of chemical species which we would expect might be present in the atmospheres, secondary atmospheres that we consider. And in particular, we focus on the ones which have spectral features in the Miri range, because that's the kind of data that we're considering. And so the species which we think about in our retrieval models include water, N2, CH4, CO2, O2, and O3, as well as hydrogen. So for anyone who isn't familiar with the retrieval method, I'll just go through that now in this flowchart. The idea is that we have this model of the atmosphere with various different input parameters, and the model calculates radiative transfer through the atmosphere for a given temperature profile and chemical composition. And that results in the thermal emission spectrum excuse me, being calculated. That model spectrum can then be compared to the data using a Bayesian inference algorithm. And that in turn gives us our posterior probability distributions for the different parameters of the model, which of course include the abundances of the different chemical species which we include in that model. So in this case, for the data, we're actually using simulated JWST data, specifically MIRI, and we calculate these model true spectra using the self-consistent forward model, which I mentioned in the early part of the talk, an adaptation of that for secondary atmospheres. So this is based on the Genesis code. And we use Pandexo to calculate the uncertainties on the simulated data points. We also include opacity due to the molecules, which I mentioned in the previous slide. And for the parametric temperature profile in the atmosphere, we're using that of Madhusudan and Seeger 2009. So first of all, we wanted to test this retrieval framework on a particular case. And so we chose TRAPPIST-1b and simulated its spectrum, assuming a sort of CO2 Venus-like composition that's cloud-free. And we chose to assume 30 eclipses with MIRI LRS. And so here you can see the simulated data. This has been binned down, and that's also the case in some future plots as well, just to make it easier to see the data. But in the retrieval, the spectrum is at the native resolution. And so we can see that the retrieval is able to fit the data pretty nicely, as well as the temperature profile, especially in the photosphere, which is what we would expect. And in this model, the 3 components that we include are CO2, H2O, and N2. These vertical dashed lines show the input values. And we're able to correctly infer the presence of H2O and CO2. N2 isn't constrained because it doesn't have the spectral features we need to detect it. And we're actually getting 5 sigma detections of both CO2 and H2O here, which is consistent with the findings of Listic et al. 2019, given the 30 MIRI LRS eclipses that we've used.
And Anjali, really quickly, you have 2 minutes.
Awesome, thank you.
Of course.
So moving on, we also wanted to expand this to other planets and other atmospheric compositions. So on top of TRAPPIST-1b, we've also considered GJ1132b and LHS3844b. And we're considering the CO2-rich Venus-like atmosphere from before, 50% CO2, 50% H2O atmosphere, and 100% H2O composition as well. And when we're looking at these spectra, we sort of wanted to have a hierarchy of questions that we ask, as if we really have got this data from JWST. What would be the first questions that we would try to answer with that data? So the first one is the spectrum consistent with a bare rock? This is discussed in Colotel 2019, and essentially a bare rock scenario would not have energy redistribution from the day side to the night side, whereas an atmosphere can have that energy redistribution. And so we can tell the difference between the two different scenarios, so the colored lines versus the solid gray line. On the other end of this wish list is obviously detecting specific molecules like CO2 and H2O. So for example, this very sharp feature at 9 microns is due to CO2 and really helps to detect that in this wavelength range. But in between these two extremes, we can also ask, are there any spectral features, even if we can't assign them to any particular species? And we find that in some cases, that is a useful question to ask, and the retrieval is able to identify that the spectrum is not a black body, even if it can't tell us exactly which species is causing that absorption. And I'll come back to that in a moment. So just as I wrap up, very nearly done now, the conclusions of these different retrievals and this exploration is that for LHS3844b and GJ1132b, we found that with 8 Miri LRS eclipses, we could get at least 4 sigma detections of CO2 and H2O for the Venus-like case. And if we increase that to 20 eclipses, we can actually detect CO2 and H2O at least around 4 sigma in both the Venus-like case and the 50% CO2 and 50% H2O cases. For TRAPPIST-1b, as I mentioned before, with 30 LRS eclipses, we can characterize the Venus-like case, and we find that we can also detect CO2 and H2O in the 50% CO2, 50% H2O cases as well. And as I was just mentioning, in the 100% H2O case, we find that it's actually quite challenging to detect the water in some of these cases. But there are cases, for example, for 20 LRS eclipses for LHS3844b, for example, where water isn't quite confidently detected, but we do have a 4 sigma detection, if you like, of some kind of absorption. So that's also a useful thing to get out of the retrieval. So I think that's my time. So I will leave my summary slide up and I welcome your questions. Thank you.
Awesome. Thank you so much, Anjali, for your talk. Yeah, we'll jump right into questions. We have a question here from Ryan McDonald. He says, "Hi, Anjali, nice talk. Why does the prior density for this implementation of the centered log ratio transform tend to 0 as the lower mixing ratio limit is approached? This can lead to artificial lower limits for the molecules not present in the atmosphere, example O3.
So if I'll try and rephrase the question to see if I understood correctly. So I think my screen stopped sharing, but I'll try and bring it back up. There we go. So I think it's this slide. Okay, yeah, so at this end, yeah, so in this parameterization, obviously you can assume that the minimum amount of a certain species is 0 and the maximum is 1, but that leads to sort of infinite bounds, if you like, in this transformed space. And so to keep it finite, we basically assume that the minimum abundance for a given species is 10 to the minus 12. At that point, we wouldn't actually detect any of those features in the spectrum. So that's sort of safely lower limit. And yeah, correspondingly, the maximum abundance that you can have is 1 minus 10 to the minus 12 times the number of molecules in that you include. And so those are the values in abundance space that we have as the 2 limits of the prior, and then that gets transformed into this CLR space.
Okay, great, thank you. And so we have another question from Eliza Kempton. She says, "Thanks, Anjali. For your sub-Neptune modeling, do the aerosol properties assume a particular composition, hydrocarbon haze, KCl clouds, etc., or are they pure Rayleigh scatterers?"
That's a great question. Yeah, so in this case, we've chosen a very simple haze model. So we're actually just taking a hydrogen Rayleigh scattering and boosting it by a constant factor. But looking at more realistic haze compositions is something that I definitely want to look into in the future.
Okay, great. And I guess I have a question. You just mentioned sort of at the end, and I guess right before this, Zafar, if you could prepare your slides and your face cam. But you mentioned at the end that you wouldn't be able to detect water with high significance. Is that just sort of a matter of, I mean, would you be able to detect it with another instrument, or were you just talking about Fermieri specifically?
So with enough eclipses, you would be able to detect it. And there is actually a case, I sort of skimmed over this, but for GJ1132b with 20 Miri-LRS eclipses, we do find that you could detect water in that case at about 3 sigma.
Okay.
So yeah, so that's at one point. So it's more that with a kind of reasonable number of eclipses that we've considered here, it's a more challenging species to detect compared to CO2, because CO2 has that really sharp feature at 9 microns. And because water has a bit more of a sort of broader continuum absorption, it makes it a little bit trickier. I think actually high res would be an interesting route to take for that, because obviously water has a very dense sort of forest of lines. So maybe that would be a cool way to do it instead.
Yeah. Okay, great. Yeah, thank you so much.
Thank you very much.
Okay, great. And so with that, we'll move on to our next speaker. And so our next speaker is Zafar Rustamkulov, who is at the who's at Johns Hopkins University. And so with that, Zafar, take it away.
Sorry, couldn't find the unmute button there for a second. Thank you so much for the introduction, and thank you to the CHAMPS collaboration for organizing this conference on such a short notice. I'm Zafar, a third-year PhD student at Johns Hopkins University, and today I'll be telling you about some work that I carried out with my advisor, David Singh, and my excellent undergrad mentees, Rongrong Liu and Ashley Wang. But before I get into it, I'd like to first reflect on the wonderful progress we're making with JWST's deployment. We can finally breathe a sigh of relief. The motors are moving, clamps are unclamping. Every stage so far has proceeded normally, and I'm so excited. Nominally, we'll have something like 180 days before science, and I'm really looking forward to it. In this talk, I'll be telling you about my work studying the characteristics of one instrument aboard JWST, perhaps my favorite one, NIRSpec. NIRSpec will be a workhorse for our field. Of the 40 accepted Cycle 1 time series proposals, I counted 24 that use it. That's 60%. Something like 5% of all JWST science this cycle will be exoplanets with NIRSpec. Even the challenging, exciting targets TRAPPIST-1E and D are slated for G2 observations with the PRISM mode. So why do we like NIRSpec so much? Well, it's got a really broad wavelength range. There are 7 observing modes at different resolutions. The wavelength coverage will overlap with many information-rich carbon and oxygen-bearing species. NIRSpec's G395 mode pairs really well with NIRS-SOS, as detailed in Battalion Line 2016. And another reason I like NIRSpec so much is because my collaborator Jess Spake and I are co-PIing a small Cycle 1 program to look at the thermal structure of a warm Saturn. In this talk, I will tell you everything I've learned about NIRSpec's noise properties from a lab-measured time series. So in 2016, NIRSpec was put in a cryo-vacuum chamber for 3 hours to carry out a bright object time series observation of a faint LED. 12,000 spectra were obtained throughout the exposure to test the instrument's stability, noise performance, and intrapixel systematics. The light source was violently shaken by about 15 milliarcseconds or 0.1 pixels, and it flickered at the 0.1% level. The lamp spectrum is riddled with spectral features of frost freezing out of the air onto the LED, with 2 prominent ones sticking out in this GIF. Here I'm showing the first 40 integrations of the time series on a log stretch. A strong time and frequency dependent undercurrent of noise can be seen in the unilluminated region of the detector above and below the trace. This is called 1/f noise, with f being frequency. You can see how messy the white light curve is too. The systematics in this data set are strong and very wavelength dependent, but we can use this worst case scenario to our advantage to map out how to best deal with systematics and how to prepare for the real thing. So in the upper right figure, I'm plotting the uncorrected mean normalized spectrophotometry. And you can immediately see the signatures of lamp flickers, frost deposition, and even trace jitter imprinted into the photometry. And in the figure below, we can see that the jitter, or the X and Y shake of the detector, or the source on the detector, is about twice as bad as what might be expected of real JWST data. So this really is a worst case scenario. In order to deal with all these systematics and to distill the detector's performance, we created a fast end-to-end reduction and analysis pipeline that goes from raw data to atmospheric spectrum in minutes. We use the pipeline to simulate a real near-spec exoplanet time series and perform an injection recovery test on the spectrum of the well-known exoplanet GJ436b. In this process, we gleaned some important insights into the instrument's performance.
As Zafar, really quickly, you have 2 minutes.
Great. So we clean the spectrophotometry to reduce the impact of lamp flicker in a careful manner that doesn't introduce self-correction. And we measure the systematics at each wavelength with a simple linear regression fit. Right away, you can see how wavelength dependent the trends are, but thankfully, using a joint fit, we were able to detrend most of them out. The systematics model is composed of a sum of the X and Y shake vectors, their second order terms, the common mode, and a linear slope term. So here's our extracted transmission spectrum. For the most part, we do well, except for a few spots where the lamp's frost deposition curve is concave through time, which adds bias to the transit depth, and is pretty much impossible to reliably detrend in this case without some kind of self-correction. Now, if we select a bin in a region of the spectrum that isn't riddled with flicker noise and weird ice features that are forming and changing, we can peer through the systematics and catch a glimpse of the detector noise floor. So that's what's shown here. Highlighted in tomato at 4 microns is the optimal bin to try to see down to the noise floor. The wider bin brings down the white noise and brings up the relative contribution of the flicker and systematics noise. You can see that the detrending vectors here on the bottom right are on the order of a few hundred ppm, meaning this is a fairly noise-free part of the spectrum. In the top right panel, you can see that the white model does a pretty good job of capturing the bumps and wiggles. Now let's zoom in on the bottom left panel here. This panel shows the scatter of the residual of the model fit as a function of bin width. A healthy curve that is free of residual systematics and noise sources follows the 1/√n dashed line, or the photon noise limit. And that's what we're seeing here. In principle, we can follow this curve all the way down to the detector noise floor, but it doesn't look like we're hitting it. Our curve closely follows the photon limit down to around 20 ppm, where we start to run out of counts to bin. This is good news. We can pretty confidently say that the noise floor is less than 20 ppm. The yellow line contains a fit to a noise floor, and it looks like it's consistent with perhaps just a few parts per million. But again, we don't have quite enough counts to be sensitive to that level. So noise floor aside, what kind of jitter systematics can we expect from our upcoming web data? Long story short, about 100 ppm from X jitter and 300 ppm from Y jitter, imparted on the undersampled near-spec PSF. We're finding that these jitters can be mitigated very effectively with first and second order polynomials in our systematics model, and this is great news. So in summary, we find that the jitter systematics should be small and easily mitigated. The noise floor is likely below 20 parts per million. We generally recover near photon precision, and the 1/f noise, which nearly doubles the white noise, should be removed at the very first stage of reduction. This all bodes very well for transmission spectra of challenging targets with atmospheric features at the tens of ppm level. Lastly, I wanted to mention that the data is publicly available on the ERS website, and I recommend it as a useful learning tool for future JWST users. Thank you for your time, and I will take questions.
Awesome. Thank you so much, Zafar. Our first question is from Kevin Stevenson, who asks, in your jitter correction, was the XY cross term insignificant in your fit? I didn't see it in the figure.
Yeah, not very significant. I actually pulled it out of one of the figures just to make it less cluttered. Yeah, not very significant, but useful.
And I guess just a quick follow-up from him. He says, outside of polynomials, have you explored more complex jitter correction models?
Yeah, we're about to do that. We might look into an exponential model. We might want to be using a third order polynomial as well, but we're just going to explore all those things, and that'll all be in the paper soon.
And then, Katherine, if you could prepare your face cam and slides. And then we have another question from Jacob Bean, who asks, how does the size of the spatial jitter compare to the size of the near spec slit?
Yeah, so I think some of the jitter systematics are actually from slit losses. The jitter is about 0.1 pixels, which is 15 milliarc seconds, and I think that's smaller than the slit width. I'm pretty sure it's smaller than the slit width by a factor of 10 or 100, but I'm not positive. The jitter is about 1.5 arc seconds. So yeah, factor of 10. Yeah, thanks, Jacob. That's the question.
Okay, great. And so with that, thank you, Zafar, for your talk. And we'll move on to our next speaker, Katherine Bennett, who is a second-year MA student at the University of Wesleyan. Katherine, take it away.
I also couldn't find the unmute button for a moment. Thank you. Can you guys all see my screen okay? Okay, perfect. All right, so thank you so much for that introduction. As Jason said, I'm a second-year master's student at Wesleyan, and I'm going to be telling you about the work that I have done so far in my thesis in the search for helium in the extended atmosphere of the hot Jupiter WASP-48b. So just like in Yoni's talk, he was mentioning, this line of helium 10-830 angstroms, which has become a prominent indicator of atmospheric escape. When these planets are very close to their host stars, they're highly irradiated, and this can lead to the outer atmospheres heating up and escaping, leading to a measurable mass loss and possibly a driver of planetary evolution. So that's why it's a really exciting question right now. Why this 10-830 line of helium? For a long time, Lyman alpha was actually used as a marker of this atmospheric escape. However, helium is not as affected by the interstellar medium absorption as Lyman alpha. And in addition, helium can also be used using ground-based telescopes. So we can use these high-resolution spectrographs to get some good data on this line. This absorption feature has been predicted since the beginning days of transmission spectroscopy back in Seeger and Zaslav 2000, but it actually wasn't detected until 2018 by Spake et al. And since then it has exploded. There have been about 20 detections and non-detections in the literature since this paper, and I'm sure there are going to be more coming out in the next few months. This paper, this graph that I have for you on the right is an image from one of the theory papers that was written in 2018 by our collaborator Antonio Oklicic and Harada, 2018, showing this predicted absorption in a couple of exoplanets. And so you can see that there are kind of two absorption features that we see. It's actually a triplet. This line is actually a triplet, but the two lines are so close together that typically you just see this one big feature over here, and this smaller feature to the left typically isn't seen in observations. So the planet we looked at was WASP-48b, which is a hot Jupiter that has a larger radius than Jupiter itself at 1.7 Jupiter radii. It orbits at 0.034 AU from its host star, so its period is only 2.14 days, making it a prime target for atmospheric characterization. It orbits around an F-type slightly evolved star, which is what makes it kind of interesting, because we think right now that this driver of atmospheric escape is the amount of EUV flux coming off from the host star, which is in turn thought to be due to stellar activity, which probably decreases as a star ages. However, this star, though it is older, it rotates actually a lot faster than expected. We think that its planet has actually spun up the rate of rotation. So it provides an interesting opportunity to look at this question of, maybe it is older, but perhaps it actually has higher stellar activity than anticipated because of this higher rotation rate. So the data were collected from the Habitable Zone Planet Finder spectrograph of the Hobby Eberly telescope in Texas. And the way this telescope works, you can't like look at one spectrum over the course of the whole time frame. So we have three transits from 3 different nights, and in total data from 7 different nights. So 3 in transit and 4 nights for out of transit. We had a total of 32 different exposures at the end of the day, and each of them looked something like this. Once we applied all of the velocity corrections that needed to be applied, we found that lo and behold, our helium lines were, lo and behold, our helium lines were smack in the middle of this OH doublet right here. This is a telluric emission line from the Earth's atmosphere, as is this. Can you see my mouse?
Yeah, and just by the way, Katherine, you have 2 minutes.
Okay, perfect, thank you. These are also telluric absorption lines, and this is our one silicon stellar feature that we see here. So our main kind of bugaboo this whole time has been, how can we really get rid of these telluric emission lines? So after we went through the data analysis process of removing the stellar continuum and weighting the data and subtracting these lines, you can see that in some exposures, our subtraction techniques worked pretty well. We still have this silicon feature. This is kind of just zeroing in on that area. And you can see a remnant of a helium line here. This did not work so well for all of the exposures. You can see here that there's kind of this like echo of that OH doublet here. So I'm still in the process of figuring out exactly how to best subtract those telluric lines, because I don't want, I don't want to really go in and wiggle and adjust a lot of stuff for fear of losing any data, because that's really where we want to hone in and look at. But for right now, once we weight and then add all of these exposures together to create a final master in versus out of transit spectra, we can see that we don't see any helium detection in this planet. Here is our in versus out of transit spectrum. So again, we still have this feature that will work to eliminate here, but when we do create our final transmission spectrum and divide the in versus out of transit spectrum, we can see, in fact, that it's pretty flat, and that when we compare it with Antonia's model, the expected absorption feature is pretty small and is constrained, within the noise. Oh my goodness, I'm sorry, within the noise that we see. So, our next steps are really going to be, one, how can we kind of constrain what we would expect the AUV flux to be from this star, because that flux is really what's going to drive the parameters from this model. And then from there, again, what does this say in the context of all of the helium exposures that we've seen to date? So thank you so much. Thank you very much for all of our organizers, and special shout out to Aaron. Really appreciate you guys giving us this opportunity. And thanks so much.
Awesome. Thank you so much, Katherine. Yeah, thank you so much for your great talk. I guess I could start with the first question here. Do you have any plans for any follow-up observations in the near future?
Not yet. That would be very exciting. I think if there is no helium, if there's no helium detection here at this planet, I think at this point, I'm excited to do this again with some other targets. And I think what is cool is that this data were collected back in 2018, 2019, which is kind of before people really started honing in on like what types of stars do we expect to see this signature around. So now that we have a better idea, that I'm really hoping to use our answer here and in the context of all the helium detections to date to hopefully, guide some future observations of new targets.
Makes sense. Thank you.
Mm-hmm.
I guess if no one else has a question, I can ask another question.
Sure.
Can you, I guess, tell me a little bit more about, you said there was like a silicon feature in the data.
Yes.
Do you know, could you, I guess, speak to a little bit more of where that comes from?
Yeah, so I think this is just a pretty expected stellar feature to see at this wavelength. I've seen it across almost all of the stellar spectra that are looking at this very specific region. So it has just been a good kind of grounding for me to say, okay, yes, there's my silicon line.
Okay, that makes sense.
Yeah.
Okay. Okay. And so I think with that, thank you so much again, Katherine, for your talk, and I will move on to our next speaker.
Thank you all.
Our next speaker, Peter Smith. So yeah, Peter, if you can prepare your face cam and slides.
All right. Can you see that?
Yeah, yes, I can. Take it away.
Okay, excellent. So, hi everybody. My name is Peter Smith. I'm a graduate student at Arizona State University. And today I'm going to talk about combined high and low resolution retrieval of a hot Jupiter. So hot Jupiters are interesting objects to study because there's nothing quite like them in our solar system. So these are gaseous planets, really close in orbits, very short orbital periods. And usually when we study them, one of the things we want to find out is how did they get there? We know they could not have formed as close to the star as we observe them to be today. So they must have formed further out and migrated inward. So when we measure the compositions of their atmospheres through spectroscopy, we try to form some useful metrics that we can use to compare to predictions made by planet formation models. So these are usually things like carbon to oxygen ratios and metallicities. So this study focuses on a hot Jupiter called WASP-77AB. Here's some parameters, and we do thermal emission. So this is day-side emission from this planet. So hot Jupiters have been studied extensively both in space and from the ground. Both have their advantages and disadvantages. In space, no one can hear you scream about telluric interference. So obviously there's no atmosphere that you have to worry about. However, you are limited by what you can shove into a rocket. So usually these instruments have very low spectral resolutions, maybe 100, 200 or so. And current instrumentation has relatively limited wavelength coverage. However, space-based low-resolution exoplanet spectra does retain continuum information, and also you can look at it by eye, which is a nice thing to be able to do. From the ground, in the near infrared, you have to deal a lot with telluric contamination, so absorption and emission from the Earth's atmosphere, but you can have quite high spectral resolution from the ground, anywhere from 20,000 and up all the way up to like 100,000 on some instruments. And this high spectral resolution actually enables us to bypass the telluric contamination because we can resolve individual molecular lines from a planet's atmosphere, and we can also resolve those lines Doppler shifting as the planet moves in space around its star. So if you take a sequence of spectra of a planetary system and stack them in time, you'll see, like in this cartoon here, that the molecular lines of the planet will trace out a sinusoidal pattern. And because they're not constant in time, you can use that fact to separate the planet signal from the things you don't care about, like tellurics, through various detrending algorithms, things like principal component analysis, or PCA. So like the basis of PCA is that you can take this spectral sequence and split it into the main principal components that make up this image. And the first few principal components will be things that are dominant in your observation. So like latest function of the instrument, telluric interference, even the stellar spectra. You can take those out. What you're left with is residual noise, and the planet signal is buried there in residual noise, which is why I said you can't really see your planet spectrum at high resolution. Usually we have to do cross correlation methods and template match atmospheric models with our data to try to place any constraints. Also, most importantly, ground-based telescopes cannot be dropped, unlike other things. So we did 3 retrievals in this study. And like I mentioned before, this is all thermal emission. So we did a high resolution retrieval using the IGRINS instrument on Gemini South. This has a resolution of about 45,000. We have 3 nights, both pre and post secondary eclipse. The PI of the observant program is Joe Zaleski, who, by the way, is on the postdoc job market, so you should hire him. We also did a retrieval on Hubble WIFC3 data, courtesy of Megan Mansfield, and she has a paper that goes into more detail about this data set coming out later, so you should read that. and also a third retrieval that combines these two data sets into one retrieval framework. And so we can see here the Igrins data set is in blue. We get really nice, precise constraints on both gas abundances and the thermal structure of the atmosphere. In red is WFC3, not quite so precise, but that's to be expected. And in green is the combined retrieval. And you can see the Hubble doesn't really add much gas information, but because it's that low resolution spectrum still has continuum information, we can actually really more precisely constrain the thermal structure in the atmosphere.
And also, Peter, really quickly, you have a minute or two left.
Okay, great, thank you. And also, because we have a low resolution data set, we can actually compare our high resolution fits to that data by eye, which is something you can't always do at high resolution in the near infrared. And as you can see here, it's a really nice, beautiful fit, which is always nice to see. So main takeaways, we can calculate those metrics that I mentioned earlier, C to O, metallicity, and compare them to predictions made by various formation models. And our C to O metallicity don't quite fit into any broad predictions, but that's okay. There might be something not considered, but it'll be really interesting to see how we're in this new paradigm of precisions that we can get using instruments like Igrins. And so it'll be really great to observe even more hot Jupiters with instruments like Igrins and also these combined high and low resolution data sets and start to fill out this parameter space. And so I think it's a really exciting time to be doing things like this. And of course, high and low resolution combined is a really powerful way to probe atmospheres in their entirety now. And I'll now take any questions.
Okay, great. Thank you so much, Peter. And so we have our first question from Haley Belts. It says, great talk. Could you say a little bit about the model atmospheres you use for the high resolution portion of the work? That's also a question that I had.
Yes, that's a very important aspect. So yeah, these are parametric models. So there are different, so it uses an analytic TP profile and then uniform priors on all the gases. So it's not self-consistent grid models or anything. If you want to check out self-consistent grid models of this planet, you should look at Megan's paper. And I think Lindsay Weiser is giving a talk about it later, about self-consistent grid models. So check those out. But yeah, this is a parametric model.
Okay, great. And I guess how does that differ from, I guess, a low resolution retrieval? If that
in terms of the
yeah, I guess, yeah.
Well, I use the same model both for the high resolution data set and the low resolution data set, which is why I was able to do this combined retrieval. Where the difference comes in is how you calculate your likelihood function. So for low resolution data sets, typically you can just do like a simple chi-squared, but you can't do that on high resolution because we kind of nuke the data through PCA. So there's been various ways to kind of map from cross correlations to log likelihood space and stuff. Gotcha. But now that that's possible, you can just kind of combine the two into one framework.
Gotcha. Okay, yeah, thank you. That makes a lot of sense. Okay, great. Yeah, I guess if we have no other questions, thank you to all the speakers for giving such great talks. And I'm not sure if Kevin or Aaron or anyone wants to say anything, but I guess yeah, we'll go on a break now and be back here in I guess 10 minutes for session 2. Yeah, I'm not sure if anyone else wants to say anything.